In this part of this lesson, we are trying to discuss the chemical properties of halogenoalkanes. Under chemical properties of halogenoalkanes, the very first thing I would like to talk to you is regarding their reaction mechanism. How can they participate in a chemical reaction? In what sort of mechanism? I will discuss a reaction like this. We have CH3, CH3Cl, chloromethane. This chloromethane is able to react with OH minus, hydroxyl ions. If you give proper conditions for this, we can see CH3, OH, and alcohol is formed. And chlorine Cl minus is going to go away. Okay, so this is how a reaction occurs, a general reaction to explain the reaction mechanism or chemical properties of halogenoalkanes. Here what happened was OH came inside and chlorine went out. This OH negative, if I draw over here, it is OH. The whole thing has a negative charge, and oxygen has 3 lone pairs of electrons. Similarly, if I take Cl minus, Cl minus has 4 lone pairs of electrons. Remember, any species having lone pairs of electrons can donate these electrons. This sort of substances are called nucleophiles. What are nucleophiles? Nucleophiles are substances which contain lone pairs of electrons. And these electrons can be donated. Having that in mind, I go to this CH3Cl molecule. In this CH3Cl molecule, we have carbon, hydrogen, hydrogen, hydrogen. And there is chlorine. Remember, I told that there's a polarity in the carbon halogen bond. Accordingly, I can do delta negative on chlorine and delta positive on carbon. Now this carbon is getting this delta positive charge not because it likes, but because chlorine is pulling electrons. Chlorine is pulling the bond electrons away from the carbon. So carbon experiences an electron deficiency. In other words, carbon doesn't have enough electron density. If an atom like carbon becomes positively charged because something else is pulling electrons away from it, that carbon center is unstable. Why unstable? Because it has lost electrons. Some other person is pulling electrons away. It is not happening with willingly. So this carbon is unstable. Therefore, in the medium, if you have OH minus, I said OH minus is a nucleophile. Because the carbon which is unstable in the chloromethane molecule needs electrons, this OH negative can give a pair of electrons to carbon. When this oxygen gives a pair of electrons to carbon, carbon already has 4 bonds. When this OH makes a new bond, carbon is going to have 5 bonds. It will be again unstable. So when OH negative gives electrons this unstable carbon center, this carbon-chlorine bond is going to break. And the pair of electrons in the bond are given to chlorine atom. As a result, you will get Cl minus going out, having 4 electron pairs, lone pairs of electrons. Plus, when OH comes into the carbon, I can write HO, carbon, hydrogen, hydrogen, hydrogen. When you look at this reaction, I can say one thing for sure, that the reaction shown by halogenoalkane is not addition, it is a substitution reaction. What's the meaning of substitution? One atom comes in, another atom goes out. Again, when one atom or a group of atoms come into a molecule, an atom or a group of atoms go out, allowing that species to give electrons. It's a substitution reaction. This is called nucleophilic substitution. Halogenoalkane show nucleophilic substitution reaction. Why do we call it nucleophilic substitution? Because a nucleophile comes in and a nucleophile goes out. OH negative is a nucleophile, it comes in. Cl minus is a nucleophile, it goes out. So it's a nucleophilic substitution reaction. Remember, the chemical reactions shown by halogenoalkanes fall into the category nucleophilic substitution. This note shows under chemical properties of halogenoalkanes. As discussed before, the carbon X bond means carbon halogen bond in halogenoalkanes is polar. The positively charged carbon atom is unstable and attracts nucleophiles. I have given the meaning of nucleophiles on the right-hand side. An atom or a group of atoms acts as a nucleophile if it has at least a single lone pair of electrons. And a nucleophile can donate its electron lone pairs to an electrophiles through the formation of D2 covalent bond. Some examples for nucleophiles you can take down. Examples for nucleophiles I've already discussed. OH minus. It has lone pairs of electron. Nucleophile. Chloride minus. It can give electron pairs. And I can say cyanide group. Cyanide group has negative charge with lone pairs of electrons on both carbon and nitrogen. Not only that, ammonia molecule. Ammonia molecule has a lone pair of electron on nitrogen. And what about water? Even water, because water has oxygen with two lone pairs of electrons. So they can be given. And what is the opposite of nucleophiles? Nucleophiles donate electrons. Electrophiles take electrons. A common electrophile is H+. It has no electrons, so it can accept electrons. And you know, aluminium chloride, AlCl3. Aluminium chloride has only 6 electrons around aluminum, is a nucleophile. And BH3, they are all electrophiles. Now here, for this, to explain the chemical properties of halogenoalkanes, the following diagram shows how a halogenoalkane reacts with hydroxyl ions to produce an alcohol. We have to discuss the reaction mechanism over here in this box. This is what you are supposed to show. Take down this part. I can call this a haloalkane, another name for halogenoalkane. And this is an alcohol. Halogenoalkane has go to an alcohol reacting with OH negative ions. And this is a nucleophilic substitution reaction. You are supposed to show all these arrows, charges, delta negative, delta positive, and just negative charge also. They must be shown very clearly and very correctly. If you make a simple mistake with one incorrectly drawn charge or arrow, you get no marks. We saw that halogenoalkanes show nucleophilic substitution reactions. Nucleophilic substitution reactions. If I use capital N to show nucleophilic and S to show substitution, I can write Sn to say nucleophilic substitution. Okay, the word OD is different. It's a nucleophilic substitution, but we write Sn. It's a substitution reaction of nucleophilic type. Halogenoalkanes show nucleophilic substitution reactions. However, these reactions are discussed under two categories. Two mechanisms are there. First one is Sn1. The other one is Sn2. We have to know exactly how to describe Sn1 reactions and Sn2 reactions. And the note says the reaction shown above means the reaction mechanism we have taken down over here. The note says that this is an Sn2. Sn2. There's another reaction Sn1, but this is Sn2. Why do we say that this is Sn2? Before going into that, we can just see the type of halogenoalkane present here. This is having 3 hydrogen, no alkyl groups. In my definition, I said primary halogenoalkanes contain 2 hydrogen and 1 alkyl group. This one doesn't have an alkyl group still, because there are no alkyl groups. We can call it primary halogenoalkane. Remember, I said that this is an Sn2 mechanism, and this is a primary halogenoalkane. So remember, Sn2 mechanism is shown by primary halogenoalkanes. Primary halogenoalkanes show Sn2 types of reactions. This Sn2 type of reactions can be explained in detail step by step. In order to show that the reaction between CH3Cl and OH minus is nucleophilic substitution reaction, but of the type Sn2. We will see how the reaction occurs. Product is CH3OH plus Cl minus. Always when you do construct the mechanism of a halogenoalkane reaction, be in the habit of using the halogenoalkane, showing its 3D nature. CH3Cl. CH3Cl I can show in this manner. Carbon, hydrogen. There are 4 bonds around carbon. They are arranged tetrahedrally. I'll write chlorine over here. And here we have carbon-hydrogen bond. And on the other side, carbon-hydrogen bond. Right. This is a halogenoalkane reactant, which is going to react with OH minus. Remember, I told always carbon-halogen bonds are polar. So delta positive comes over here, delta negative comes over here. Chlorine is pulling electrons. Here, see this OH minus. It has lone pairs of electrons. In fact, there are 3 lone pairs of electrons, and this structure has an overall negative charge. So this OH negative ion can act as a nucleophile. I told nucleophiles are able to give electron. So this lone pair of electron is given to this positively charged carbon atom. And then when it happens, carbon-chlorine bond breaks, giving the bond electrons to chlorine. I can draw this arrow up here also, but then because there's a delta negative charge, I decided to have the this OH coming in to make a bond with the carbon, and this chlorine going away from this molecule happen at the same time. This OH is going to make a bond with carbon, this chlorine is going to go away. I'll repeat, nucleophile OH minus enter in the molecule to join with the carbon, alpha carbon, and the chlorine removal happens simultaneously. I can draw it in this manner. I draw the carbon in the middle, show the OH coming in. It can be shown using a dotted line. That bond is being formed. And then on the other side, carbon-chlorine bond is breaking. Now, there are 3 bonds, hydrogen, hydrogen, hydrogen. On the left-hand side, chlorine is there. On the right-hand side, OH is there. Because of the repulsion given by this chlorine and OH, the 3 hydrogen atoms come in a planar manner right in the middle. 1 hydrogen, 1 hydrogen. And this has a negative charge, overall negative charge. If somebody asks, how do you know that there's an overall negative charge? You have to remember that this halogenoalkane has no charge, overall charge. But OH has a charge, negative. When a neutral molecule reacts with the charged molecule, the structure formed will have the charge of the particle. In this case, it is OH minus. So I write minus charge over here. And this structure is called transition state. So now this chlorine is in the OH is in the process of making the bond. I'll push this OH to left-hand side a little bit. And this chlorine also a little bit towards that side. And then what happens is chlorine goes out. Chlorine goes out completely. Here's that chlorine. And the carbon atom forms a bond with OH. Here's that. And the 3 hydrogen atoms, they arrange around the carbon atom in the tetrahedral geometry. This is the end of the reaction. In this reaction, the chlorine atom goes out when OH comes in. If OH doesn't come in, Cl- will not go out. Because of that, I say that for this reaction, both halogenoalkanes and the nucleophile are equally important. If you don't bring the nucleophile towards the halogenoalkane, this reaction will not happen. Because both the nucleophile and halogenoalkane are equally important for this reaction, we call it Sn2. 2 means, simply you can get the idea, there are 2 species participating in the reaction initially to carry out the reaction or to begin the reaction. The reaction will initiate due to the participation of both nucleophile and the halogenoalkane. Therefore, we call it Sn2 reactions. Sn2 reactions are shown by primary halogenoalkanes, primary haloalkanes, and these reactions happen through a transition state. This is a transition state. And one more thing, this whole reaction happens in a single step. So these Sn2 reactions are one-step reactions. From here to the products, reaction happen in a single step. But remember, Sn2 reactions are shown by primary halogenoalkanes, and these are single-step reactions. We can talk about this reaction mechanism step by step, like this. The carbon atom which is attached to the halogen atom has a slight positive charge due to the electron pull from CX bond. This leaves a slight negative charge on the halogen atom. Carbon, hydrogen. I'll take chlorine for this. Hydrogen here, hydrogen here. Show the delta positive charge on carbon and delta negative charge on chlorine. I want you to have this diagram drawn in this cage. And then afterwards, OH negative ions, which acts as nucleophile, donates one of its lone pair electrons to the nucleophile carbon center, nucleophilic carbon center in the halogenoalkane from the other side of the halogen atom. It means if the chlorine atom is on the left-hand side, like this, the nucleophile, which is hydroxyl ion, give electrons from the other side of chlorine, delta positive, delta negative. I can show the entrance of OH minus to donate electrons in this molecule on the right-hand side, because chlorine is on the left-hand side. So you can see the donation of electron pair. A complete arrowhead must be shown because 2 electrons are donated. When the hydroxyl group approaches a halogenoalkane, this OH comes towards the halogenoalkane, forming a covalent bond with the positively charged carbon atom. I'm talking about this carbon atom here. The halogen atom begins to get detached. OH is getting attached, chlorine is getting detached. This forms a structure called a transition state. The transition state has a trigonal bipyramidal shape. This is a highly unstable complex which cannot be isolated from the reaction mixture. So you can show the breaking of carbon-chlorine bond using dotted line, Cl, and formation of bond between carbon and oxygen on the right-hand side. I said the 3 hydrogen atoms attached to the alpha carbon are going to be arranged in a planar manner. Hydrogen here, hydrogen here. draw big parentheses, and show negative charge outside. This is a trigonal bipyramidal shape. Afterwards, finally, the halogen atom gets away and OH group becomes a part of the molecule. Let me write carbon, hydrogen, OH has come in, the remaining 2 hydrogen on the carbon atom, alpha carbon. And where's chlorine now? Chlorine has gone out, Cl minus. You can feel these things, but in the exam, for reaction mechanism, we can't give these 4 steps. We have to give a simple reaction. See, this is a single step reaction where the breaking of carbon X bond and the formation of carbon oxygen bond occurs at the same time. This reaction can be shown in an energy profile diagram with a single hump as shown below. I can show over here. A graph, energy level diagram. Assuming that this is an exothermic reaction, I draw reactants at a higher energy level, products at a lower energy level because it's an exothermic reaction. And I can draw a hump like that. And here we have reactants here products. And over here, we have transition state, TS. Transition state is on top of this graph. Rate of an Sn2 reaction depends on both the reactants in the reaction. These reactions are shown by primary halogenoalkanes and certain secondary halogenoalkanes also. Basically, we will take the idea they are shown by primary halogenoalkanes. And then we had to write the overall Sn2 mechanism. In the box, we have to write the Sn2 mechanism. I don't have to draw it again because I have already done it. Shall we take down this diagram? You don't have to have this. I'll remove it. And even Sn2, no need because we are going to draw this mechanism on the Sn2 part, on this Sn2 area. Probably, yeah, one step not necessary because we have discussed Sn2 again. I'll remove it. We know that they are shown by primary halogenoalkanes. Even single step is not necessary when you write the reaction mechanism in the exam. So what you are supposed to show is only this. Please take down this. We discussed Sn2 mechanism, if you have forgotten. Again, this is a Sn2 reaction mechanism shown by primary halogenoalkanes, and they happen in a single step process. Sn2 happen in single step. We go to Sn1 reactions now. We can draw the diagram for the Sn1 mechanism, but it's better if we can read this a little bit. Sn1 reactions are shown by tertiary halogenoalkane. Okay, this is interesting. Sn2 mechanisms are shown by primary halogenoalkane. Sn1 reactions are shown by tertiary halogenoalkane. And then the attack by the nucleophile does not occur on the halogenoalkane initially in these reactions. I think it's better if we discuss this reaction mechanism first separately and then come to this description, otherwise we will not understand much of it. Let's see how the Sn1 reaction mechanism occurs. To discuss this reaction, I will use a halogenoalkane having chlorine atom on one side, and let's say I'll make it CH3 here, CH3 here, and CH3 here. This is a very clear tertiary halogenoalkane because alpha carbon is attached to 3 alkyl groups. There are no hydrogen atoms attached to alpha carbon. I'll start to work with the stereo structure for this halogenoalkane. I'll write the chlorine on the left-hand side, and CH3 is up here. There are 2 CH3s towards the right-hand side. Here those 2 CH3 groups are. I told that carbon and chlorine bond is going to be polar. So we have delta positive and delta negative. In the earlier case, when this molecule, when halogenoalkanes react with OH group, the OH group, the nucleophile, attack the positively charged carbon center on the opposite direction of the carbon-chlorine bond. However, this reaction cannot happen in this manner. It doesn't happen. Why doesn't it? It's because now, theoretically, now when you look at this structure, you can say, all right, OH negative is going to give electrons to positively charged carbon atom and remove this chlorine. It doesn't happen. The reason is the 3 CH3 groups on the right-hand side is covering this entire side. This part is shielded. No one can enter. Not because of anything else. The 3 CH3 groups block this right-hand side. So there's no room for OH to come in. Therefore, I had to take this OH out from here because it doesn't react in that manner. In Sn1 mechanism, in Sn2 mechanism, OH attacks the positively charged carbon atom. Here it doesn't happen. However, when this OH negative react with this tertiary halogenoalkane, the reaction occurs producing an alcohol. Here also an alcohol is formed. CH3, CH3, OH. Right. See carefully, the OH is not going to attack this. However, the reaction has happened. How is this happening? It happens in this manner. If OH has to come in, chlorine has to go out. There's another mechanism for this halogenoalkane to remove chlorine before OH negative comes in. It is because of positive inductive effect. Positive inductive effect means the ability of an alkyl group to donate electrons to a positively charged carbon atom. There are 3 CH3 groups. So this CH3 group gives electrons through positive inductive effect. This CH3 gives electrons. This CH3 also gives electron. Now what happens? Because these 3 alkyl groups donate electrons, the positive charge on the carbon atom decreases, and then this chlorine atom is taking the electrons away from the carbon and goes out. So what happens? Cl minus goes out, but OH never came in. When this chlorine goes out, carbon gets how many bonds? 1, 2, 3. Carbon has 3 bonds. So these 3 carbon bonds organize around the carbon atom in a planar geometry. I will just draw one single plane. It's easy to understand this concept if I draw the structure in this plane. We have carbon in the middle. There are 3 CH3 groups. One CH3 group is above. One CH3 group is on this side. And the other CH3 is behind the screen on that side. Now, because carbon has lost that carbon-chlorine bond, it is having a positive charge. This structure is called carbocation. In the Sn2 mechanism, what was the product form? Transition state. Here, carbocation. This carbocation is called a reaction intermediate. I will write reaction intermediate. Not transition state, intermediate. Reaction intermediate. Reaction intermediate is a carbocation. Let me take this reaction intermediate word down so that we can have some space. Reaction intermediate. Now, because this structure, the carbocation or the reaction intermediate is flat, there's no steric hindrance. Steric hindrance means there's no problem with the space. This OH can easily donate its pair of electrons from here to that carbon atom. As it happens, you can see carbon. OH is going to get attached over here. And there are 3 CH3s. I can do 1 CH3 up here, 1 CH3 over here, 1 CH3 over there. Now the reaction is over. However, this reaction occurs in a 2-step reaction. This is step 1. This is step 2. I can show this Cl minus over here. So OH negative comes in, Cl negative goes out. This reaction happens through a carbocation. Carbocation is a reaction intermediate. Sn2 mechanism is happening in a single step. Sn1 reactions happen in a 2-step process. And Sn1 reaction begins with the releasing of chlorine or with the elimination of chlorine as a chloride ion. It is helped by the positive inductive effect of the alkyl groups. We call it Sn1 because it's a nucleophilic substitution reaction. Even though there are 2 reactants, halogenoalkane and OH minus, the reaction begins to occur without the help of the OH minus. OH minus help is not necessary at all. This reaction happens mainly because of the involvement of the halogenoalkane. So we simply write Sn1. In Sn1 reactions, only one reactant is going to help you to do the reaction. And there are two-step reactions. The reaction occurs through a carbocation or reaction intermediate formation. Here. Sn1 reactions are shown by tertiary halogenoalkanes. We read this earlier as well, and certain secondary haloalkanes. The attack by the nucleophile does not occur on the haloalkane initially in these reactions. This is because the entry of it to the nucleophilic carbon center is blocked by bulky alkyl groups. Why don't you show that in this carbon? I'll write R group here, Cl over here, one R group here, another R group here. Even though we have delta positive and delta negative charge separation, a nucleophile, I show Nu nucleophile having lone pair of electron, it cannot give electron to this positively charged carbon center. No way, it doesn't happen. You can show this, and also by cross here, we are telling that nucleophile is not attacking the molecule. Instead, these alkyl groups help the releasing of the halogen atom as a halide ion with the help of their positive inductive effect. So Cl minus comes out because of the positive inductive effect. And you can show the R group, second R group, and third R group. Carbocation is here. Cl goes out, a planar carbocation is formed. And I'm talking about positive inductive effect. We had write something about positive inductive effect. Positive inductive effect is about the ability of an alkyl group, to donate electrons to a positively charged atom to which the alkyl group is attached. If there are more alkyl groups, there is a higher collective positive inductive effect. Positive inductive effect increases when the alkyl group becomes bigger. We can show it. CH3 has a positive inductive effect. It is smaller than the positive inductive effect of CH3, CH2. And this has a lesser positive inductive effect then CH3, CH2, CH2, etc. Please complete this. Let's start the work again. Once a chloride ion has left the molecule, a structure called carbocation is formed. The carbocation is a reaction intermediate in this mechanism. I showed the carbocation over here, but let's draw it again. Carbon, R, R, another R with a positive charge. Because this carbocation is planar, R, a nucleophile can attack this carbocation, positively charged carbon center in the carbocation, in both the directions, from the left-hand side and from the right-hand side as well. So I show here nucleophile with a lone pair of electron can attack on the left-hand side, or else the nucleophile can attack this on the right-hand side as well. See, so a nucleophile can attack this carbocation in two different directions in this. With all this information and knowledge, we'll see how we can construct the overall Sn1 reaction mechanism. I think this space will be enough. You are going to draw this reaction mechanism, Sn1. Let me clear some of this clutter over here. I don't want these things. This one is out. Yeah, you can take down the rest of the things. Step 1, step 2. On the left-hand side, we have halogenoalkane. I make it tertiary halogenoalkane. Tertiary halogenoalkane. It produces this alcohol. Let us try to compare Sn1 reaction with Sn2 reactions. Sn1 reaction versus Sn2 reactions. Push it up a little bit. Okay. I can say first for Sn1 reactions. What's the first point? I can say Sn1 reactions are shown by tertiary haloalkanes. Shown by tertiary haloalkanes. Number 2. They are two-step reactions. They are two-step reactions. Number 3. They occur through carbocations. Fourth one. Rate of the reaction depends on the concentration. Rate of the reaction depends on the concentration of the halogenoalkane. This is one reaction. Fifth one, reaction begins with the exit of halogenoalkane helped by positive inductive effect. And sixth one I can write. Nucleophile attacks not the halogenoalkane, but the carbocation. This is about Sn1 mechanism. Now we go to Sn2 reactions. This one shown Sn2 mechanism is shown by not tertiary halogenoalkanes, it is shown by primary halogenoalkanes. They are Sn2 reactions. They are single step reactions. And these Sn2 reactions occur through transition state. Transition state. These reactions occur through transition states. And then fourth one, rate of the reaction depends on the concentration of both halogenoalkane and nucleophile. Number 5, reaction begins with the attacked by nucleophile. Nucleophile attacks of the halogenoalkane. That's it. There are a few mistakes I have noted here. Nucleophile. I'll correct with the pen. Nucleophile attacks not the halogenoalkane, but the carbocation. Shown by tertiary halogenoalkanes. There are two-step reactions occur through carbocations. Rate of the reaction depends on the concentration of the halogenoalkane. Reaction begins with the exit of the, not halogenoalkane, I'm sorry, halogen atom. Helped by positive inductive effect, we can write off alkyl groups. Okay, with the help of this basic introduction to Sn1 and Sn2 reaction mechanisms of halogenoalkanes, I think you are in a good shape to start the chemical reactions of halogenoalkanes, where we talked about reactions of halogenoalkanes taken individually. There are about few reactions. We will take them one by one and see how these reactions occur according to these reaction mechanisms. It is in our next lesson.